In this example, we're solving the equation x double prime plus 6x prime plus 13x equal to 0. It's second order, it's linear, it has constant coefficients, and it's homogeneous. And so, recognizing all that, we are going to try an exponential solution. The reasoning is that when we differentiate an exponent, we get a multiple of the exponent. So we're going to get a multiple of the exponent here, a multiple of the exponent here, a multiple of the exponent here, and we're going to try to make sure that the sum of those multiples is 0, so we get 0 times the exponent, which is of course 0. And so the equation here, sometimes called characteristic equation, is r squared, two derivatives, give us two factors of r, 6r, and 13 times just the exponential with no extra r's. And so to make that 0, we look at the quadratic formula. It gives us minus 3 plus or minus 2 times the square root of minus 1. And so this will be the exponential. This is what goes in the exponential. So we're going to have e to the minus 3t times e to the plus or minus 2 times the square root of minus 1t. And so the question is how to interpret this e to the 2 times the square root of minus 1t. In the short answer is interpret that as sines and cosines. You can think of it in terms of the differential equation. We want something so that the second derivative gives minus itself, and we know that the second derivative of cosine gives minus cosine, and the second derivative of sine gives minus sine. And so from that point of view, that's the right thing to guess. And so we have e to the minus 3t, and then a sum of cosines and sines, and it's 2t that's multiplying the square root of minus 1. And so we have cosine of 2t and sine of 2t. And so that's our general solution. Now we're going to try to match the initial conditions. We're continuing to solve this second order constant coefficient homogeneous equation. We have x1 and we have a general solution, x of t equal to e to the minus 3t c1 cosine 2t plus c2 sine 2t, and we're trying to match the initial conditions. X of 0 is 1 and x prime at 0 is 1. Plugging in 0 into x, e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, and so we're just left with c1. And to calculate x prime at 0, I have to first calculate x prime. So when the derivative falls, this is a product. When the derivative falls on the exponential, I have the exponential again times minus 3 times the second factor. And then when the derivative falls on the second factor, I have the original exponential, and then the derivative of cosine 2t is minus 2 sine 2t. The derivative of sine 2t is plus 2 cosine 2t. Plug in 0 here, the exponentials will be 1. So I have a minus 3 over here. Cosine is 1, sine is 0, so I have minus 3c1. In the second vector, the exponential is 1, sine is 0, cosine is 1, so I have 2c2 times 1, and that's 2c2. Now we want to solve so that obviously c1 is going to have to be equal to 1, and minus 3c1 plus 2c2 has to be equal to 1. When we solve for the coefficients, we find that c1 is 1 and c2 is 2. And so the solution is e to the minus 3t times 1 cosine 2t plus 2 sine 2t. And that's our solution with the initial conditions x of 0 equal to 1 and x prime of 0 equal to 1. Now this solution has period 2 pi. And so if we want to write it as a single function with period 2 pi, we think that the first coefficient was 1, the second coefficient was 2, so this corresponds to an amplitude of the square root of 5, and the change in the shift from having sine of 0 equal to 0 to something else is by this angle in here. So the tangent of this angle is 1 over 2, and so the angle itself is the arctangent of 1/2. And so the solution can also be written as e to the minus 3t times the square root of 5 sine of 2t plus this angle, which is arctangent of 1/2.